Hello and welcome back. Today we're in further maths and we are on the pure core, the basic of the further maths, and we go series and we're going to use method of difference. It looks like we go Maclaurin within the same question. This is an exam question. The first one says use the method of differences to sum. This looks to infinity, this sum to infinity, and then we'll look at the part B afterwards. The sequence, or rather the series rather, in question, it's quite a nice pattern. It looks like the denominators are products of consecutive terms, 1 times 2, 2 times 3, 3 times 4, 4 times 5, and so on. And it looks at numerators is actually the sum of those terms. 1 plus 2 is 3, 2 plus 3 is 5, and so on. And we also go alternating terms there, so it goes from plus, minus, plus, minus. Oops, that should be a plus there. It's a mistake, and that should be, of course, a minus on the next term. Dot, dot, dot. Okay, we're talking about sum with using the method of differences as a hint. So clearly we need to do some kind of partial fractions. And before we do partial fractions, because we've been given the series in explicit form, it might be sensible to write it in sigma notation, I think. So let's go and try to get a general term for this. So there's my sigma. Let's use dummy variable r, and when I run it from r is equal to 1, if we need to change that, we'll change it. Let's see if that gives us a nice number. Let's not worry about the alternation at the moment. We're going to use the r is equal to 1 there, so it's going to be r with an r plus 1 multiplied. And of course, this we don't actually need to even spot that this 2 add up to the top. You can treat it in its own right. 3, 5, 7, 9, 11 is elementary mathematics. So that's going to be a 2r plus 1, which does agree. If you add those two terms, it does give you indeed this particular series, with the exception, of course, of the alternating fact. So this normally we get by, this is dead, we get by putting a minus 1 and raise it to the correct power to get the right sign. So we need positive on the first one. So if we run it in from r is equal to 1, this will return as negative. So we can either put an r plus 1 or an r minus 1. So this is now the summand of this sigma, and this should produce, of course, what we're seeing up there. So in order to use the method of differences, we need to break this into partial fractions. At the moment, I'm ignoring this the alternating term of the summand. I'm just looking at the partial fractions for this. I'm going to do it by inspection. So I'm going to say, okay, the partial fractions required for this is something over r and something over r plus 1. I can actually see straight away what they are just once, isn't it? Because that's going to be r plus 1 plus r to give me the numerator. Let's just quickly confirm it. Back cover up, r is equal to 0. We got 1 over 1. And r is equal to negative 1. So I'm going to get 2 times minus 1 plus 1 is minus 1 over minus 1, which of course is 1. If you don't know anything about cover up, please just do it the long standard way, or there's not even long, I mean it's just 2 lines really, to get your partial fractions. So this partial fractions is just merely just this term here. It doesn't take into account that. And note we have a plus between them. So how does it work now? Doing method of differences, maybe this term here, the alternating term, will sort things out. So I'm going to say the following now. I'm going to write this as an identity. So let's move that to the bottom left for reference. I'm going to use this part of the board. So the sum to infinity we're trying to find is r is from equal to 1 to infinity, 2r plus 1, r plus 1, with an alternating term. That's inside the sigma. And what I'm going to do now up here, I'm going to write my partial fractions, how this should be. So I'm actually saying 2r plus 1. Actually, I could have just rubbed off the sigma. I'm very stupid at times. r plus 1 times minus 1 to the r plus 1 is going to be giving us now this bit came, of course, from just this term, so we need to multiply each of these by -1. I'm not rubbing it to bring it closer, it's okay, I hope. And that is that. All I've done is I ignore that for the time being. This is my partial fractions with 1 over and 1 over. And then of course, because this is multiplied by the alternating term, I multiplied the alternating term with each of the two terms from the partial fractions. So what I'm going to say next is usual stuff. When r is equal to 1, this particular expression, this will go of course positive. It should be giving me of course the first term there, which is 3 positive over 1 times 2, and this of course will now be equal to positive again 1 over 1 plus again 1 over 2. When r is equal to 2, we're going to be getting 5, but careful because of course we haven't done this one. That's the 5 from here, so we got now 2 times 3, but of course when we're putting 2 in there, this will now give us -1 to the 3, so this now creates a minus at the front of this term. So minus 5, which is what we got up there, 5 over 2 times 3. Again, all of this now will go minus. It's going to be minus 1/2 minus 1/3, and so on. R is equal to 3. Now I'm doing the next line without thinking, and hopefully I'm doing it right. Substituting that in there should give me positive 7 over 3 times 4. And if I do that here, it should go positive again, 1/3 plus 1/4. One more term here. R is equal to 4. 4, of course, 4 plus 1 will give me 5, so I'm going to go negative. So it's going to be negative 9 over 4 times 5. It's going to be equal to negative for both of those two as well. We're going to get 1/4 minus 1/5, and after that, let's use a red pen, dot 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 dot, and so on. I'm gonna go, of course, let's say to what happens if we just carry on in this particular fashion. Normally would have had here an r is equal to n, and then we'll let n tends to infinity. I'm not going to do that because of course this pattern will go on forever because we're summing to infinity this particular series. And let's see what happens now with the terms that we got in here. Here of course we'll be adding that plus that plus that plus that forever, but on this side terms will be cancelling forever, like this. And of course the minus 1/5 will cancel with another positive 1/5 in there, and so on and so on. Okay, therefore the only thing that will survive with this from this table, for this sorter if you prefer it, is just this one, the 1 over 1 that we got in there. Therefore we conclude that the sum from r is equal to 1 to infinity of this particular series is in fact equal to 1, and there's nothing else to say for this particular one. How many marks should that be worth perhaps in a standard exam? I'm estimating that to, if it's given in this particular form, maybe about 6 marks, because of course it requires probably you get some marks for putting into sigma notation, for setting out your partial fractions, and then writing of course a few differences, and of course concluding correctly that the answer to this one should be 1. Okay, part B now says use the Maclaurin. I'll just try to abbreviate and I missed the word there. Use the Maclaurin expansion of the log of 1 plus x to verify the answer from part A. So essentially it will be written, perhaps it'll be better in English. It says do the same thing again, only this time do a completely different method by using the Maclaurin expansion of the log of 1 plus x. How does that help us? First of all, it doesn't say we have to derive this particular expansion. So the log of 1 plus x, it's in the formula booklets, and it is actually x minus has a lot of writers. Maybe I should write it as coefficients at the front. Let's write it as 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4 plus 1/5 x to the 5 minus dot dot dot. So this is now the Maclaurin expansion of the log of 1 plus x. How does that help us now with answering this particular problem? Okay, the answer is, as I said, probably the English might be a little bit better there, or the hints that they will be given in the question. We need part of the part A. We need the partial fraction. So that's the first thing. The second thing, this particular sigma, I'm going to write it here. We broke it using partial fractions, of course. And I think I just about remember the answer because it was so simple. So this is what we're trying to find, of course. And we said, okay, this is exactly the same as these two sums. The sum of minus 1 to the r plus 1 over r, from r is equal to 1 to infinity, plus exactly the same from r is equal to 1 to infinity, also alternating, but this was over r plus 1. We got this from the partial fraction. Of course, we didn't have the sigmas, but this is what we got, and then we used the method of differences. Now, how does that help me? How does this expansion helps me answer my problem? If we look individually at what happens in here, what kind of terms we're getting just from this particular sum, first of all. We're going to get, of course, it starts with positive. We're going to get 1 over 1, then minus a half, plus a third, minus a quarter, and so on. This comes out of this. And then if we look at the Maclaurin of the log of 1 plus x, we're getting exactly the same coefficients of x. That's a 1 minus a half plus a third minus a quarter. So it appears it'll be useful perhaps, and I'm going to use a red pen and do it just above it. I have just about enough space and say, okay, by the way, this particular one, it should be valid. It's in your formula booklet. It's between 1 and minus 1, and it should be like this. Okay, that's the radius of convergence. It works between those two values. So we're going to make sure, of course, what we're substituting in there is valid. So we're going to put x is equal to 1, which we are allowed in both sides of this expression. So we can say, okay, if we put x is equal to 1, we're going to get the log of 2 is equal to, of course, 1 minus a half plus a third. For some people, this is a well-known fact, and we don't need to actually prove or show anything in a question. Depending on how it's phrased, it might be a good idea to show some working and some justification for what you're doing. So this particular infinite series, it's a well-known fact. It's actually log 2, and this is where it's coming from. So in fact, this is what this particular sigma is. It's just this power series with x is equal to 1, and therefore we can say, okay, that is definitely the log of 2. That's a bit weird, isn't it? Because we know all together this should sum to 1, so we better cancel this log 2 somehow, otherwise we'll be in trouble. So we're coming now to the next term, the next sigma, and the first thing to see is, okay, what kind of terms are we getting from something like this? R is equal to 1, it starts with positive, but now because we go r plus 1, the first term is in fact half. Then of course it will alternate, so we're getting a half minus a third plus a quarter minus a fifth plus a sixth, and so on. Okay, this is very much related to this, but we have two problems. The first problem is we're missing this one, first of all. This one is not there. We got halves, thirds, quarters, and so on. But on top of that, we have completely messed up signs. The minus are pluses and the pluses are minuses. We got the opposite of what we got. Okay, no problem. I'm going to do the workings here as it is, a little bit sloppily, and say, all right, this particular sigma, call it capital S for sum. Okay. And I want somehow to create this series, which I know it converges to log 2. First thing, I need to sort out the pluses and the minuses. Very easy to do so. I'm going to multiply both sides of this equation by -1. So minus a half, plus a third, minus a quarter, plus a fifth, minus a sixth, plus dot 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 is clearly minus my s. Okay, then what's the obvious thing to do? I now have everything but my 1. So quite clearly, let's use a green pen for that. I'm going to add 1 on both sides of this equation. Now, if you look at what I've got on the left, this particular infinite series, it is known to be the log of 2. And that's why I've done what I've done in there. So I can say the log of 2, all of this, is equal to 1 minus the answer to what I'm trying to find. Well, evidently, my s, if I move it to the left, is going to be 1 minus the log of 2. So this particular sigma, let's put in a border as well, is going to be equal to, I'm going to write on the side, so I have no space here, is 1 minus the log of 2. Okay, and therefore, I don't want to just rub off things. It should be obvious that plus that, as we expected. I did say we expect somehow to cancel this log, because otherwise we'll be in trouble. Plus, of course, 1 minus the log of 2. The logs of 2 cancel. And again, as before, we got 1. Isn't that beautiful? How both of them, completely different methods, and they both work, and they both complement each other. I hope you enjoyed it. I hope you followed it. How many stars is this question? If you had better, I mean, at the moment, it's a problem is obviously I'm limited as to how much I can write on the board, and English is not my first language either, so sometimes struggle to actually write the question properly. But if this was written properly with good communication, I would imagine this is something like a 4-star in the usual system that I use in my papers and my books. I hope you enjoyed it again, and I'll see you very soon. Who's laughing now?